Hello everyone, and welcome to the UT Austin Portugal session at the Science Summit 2022. So, my name is Andrea, and I'm the program's executive director here in Portugal. I'm very happy to be your host for the next 1 hour and a half. I'm really sorry we had some technical difficulties, that's why we're starting a bit late. Let me tell you that we have put together a very interesting lineup of presentations that I'm sure will give you a hopeful vision for the future of energy, and will also show how the program can be at the forefront of research to speed up energy transition. So enough talk from my side. We have a lot of things to cover today. So let me kindly introduce you to Professor José Manuel Mendonça. He's the National Director of the UT Austin Portugal here in Portugal. I turn it over to you, Professor.
Thank you very much, Andrea. Good afternoon, everybody, and thank you very much for being with us. A bit late because of those technical problems. So I'll help catching up by shortening my 10 minutes to 2.5 minutes opening remarks. This year, the program celebrates its 15th anniversary. And this session at Ciência 2022 takes stock of some of its projects and assets, and will help to pave the way to a new theme which is dearest to us, which is clean energy transition. Everybody knows that energy transition tops political and business agendas on both sides of the Atlantic, and we may say all over the world. Although energy does not constitute a scientific area of the program, as you know, the Austin Portugal program is well positioned to help speed up the energy transformation, both in Portugal and in Texas. After all, it gathers advanced energy expertise, top-notch research infrastructures, scientific leadership, and the people who interface exceptionally well with both academia and industry. The present areas of the program, two of them are very well connected, very well positioned, which is nanotechnologies and advanced computing. And they may take a leading role in setting the stage for energy to become a core area of the partnership in the near future. To a great extent, the breadth of this impact in nanotechnologies and advanced computing results from the program's alignment with critical challenges also tackled by other regions of the world, not only by Portugal and Texas, but also by other regions of the world. And energy-related challenges are certainly among those. So the objective of this session is shedding light on the synergies Portugal and Texas share with this Egypt Science 2022 guest country regarding their standing and in the global energy landscape and potential to become global renewable energy hubs, and also the importance of science and international scientific cooperation to build a sustainable future for us all. So I wish you a very nice session, and I'm very much looking forward to what we will be hearing and from the presentations and also from the discussion. Andrea, and I pass to you the floor to introduce the next speaker.
Thank you so much, Professor. I think this intro just set the right tone for our session, and I'm very pleased to introduce our first speaker, Brian Corgle. Hi, Brian.
Hi everyone. Hopefully you can hear me.
Also directs the Industry University Cooperative Research Center for a Solar-Powered Future, and he also serves on the program as the area director for the area of nanotechnology. So, Brian, thank you so much for accepting our invitation to be here today. So the stage is yours now.
Great, thank you very much. So hopefully my internet is going to be okay. It seems a little bit laggy, but hear me, I can start. So it's nice to nice to be here today. So I'm going to talk about energy research at UT. So from path-breaking research to deployment of innovative solutions for a sustainable energy future. I'm the director of the Energy Institute at UT Austin, as well as the area director for nanotechnologies at the UT Portugal program. So what I'm going to present is an overview of what is happening at UT Austin in energy transition. Next slide, please. So we've got at this time there's a lot going on in terms of the future of energy. So governments are announcing net zero carbon emissions ambitions, corporations as well. So I just have two of these announcements here. ExxonMobil, for example, and Gulp as well with their net zero carbon emissions ambitions. So we have three different kinds of emissions: Scope 1, Scope 2, and Scope 3. Some companies are announcing decarbonization all the way to Scope 3, which would be the carbon emissions related to their end products and their customers. And some companies are focused on just Scope 1 and Scope 2. But right now, most major industries are looking at decarbonization. Next slide. So the question is, how do we get to an energy future with zero greenhouse gas emissions? We have some ideas, but there's a lot of research that still needs to be done, techno-economic analyses, etc. Next slide. So one thing that is not going to happen is the U.S. or the world and the U.S. is not going to decrease its energy use. So energy use correlates with economic prosperity. As economies continue to develop around the world, energy use is increasing, and with that, so are CO2 emissions. And this is our challenge because now we're facing a significant climate threat. And so, how do we reduce those CO2 emissions? Next slide. Way to do that is to increase the amount of renewable in the mix, but fossil fuels are still going to make a large amount of our energy use, around the world. So not only do we need to think about new ways of producing and using energy, but also decarbonizing our existing uses of energy. Next slide. So the way I've been thinking about this, at least at UT, is thinking about these three topical areas that we need to address to get to net zero carbon emissions. One is addressing carbon management, so carbon capture, storage, conversion, thinking about low carbon fuels, distributed energy sources such as wind, solar, so we're thinking about biofuels. I'll talk a little bit about geothermal, hydrogen, and then think about manufacturing sector as well. So how do we decarbonize steel manufacturing, cement, chemicals, petrochemicals, and that sort of thing. So these are the things we're thinking about in terms of our broad research portfolio at the University of Texas. Next slide. So I would argue that partly the reason for the energy transition is because the dramatically decreasing cost of renewables like wind and solar. And so if we look at the cost, solar, for example, it's the levelized cost of electricity without subsidy is on par with natural gas. In many locations, it's cheaper. So solar, wind are the cheapest of electricity at the moment. And so that's why we see these massive upscaling of the use of solar and wind. Next slide. These are data from Lazard's report on levelized cost of energy without subsidy. Again, if you compare natural gas to utility scale photovoltaics, they're on par, and photovoltaics in many cases is cheaper. Next slide. If we think about plus storage, so with batteries, large scale solar plus storage is coming online. It's still a little bit on the expensive side, so about 9 cents per kilowatt hour. compared to 4 or 5 cents per kilowatt hour for natural gas. but those costs are continuing to come down, and it's changing our energy production landscape. Next slide. So there are research opportunities as well as challenges related to renewables adoption. So for one thing, accessibility to large amounts of renewable power offer a wide range of decarbonization opportunities. So think about chemical processes. We can think about electrifying those processes to lower the carbon footprint. We have electric vehicle mobility, low carbon fuels, industrial decarbonization. Those are some of the opportunities. Then we have a number of challenges faced, renewables, intermittency, things like understanding price forecasting, how that fits together, seasonal energy storage, large initial capital investment, some land use considerations. Next slide. So we think about this research at UT. I direct a Center for a Solar Powered Future, in addition to directing the Energy Institute and Nanotechnologies program within the UT Portugal program. And so within this center, we think broadly about the entire value chain of the solar industry, all the way from manufacturing and materials to deployment and the integration of solar with residential power generation, for example, and e-mobility. So this is some of the research that we're doing. We have 17 industry members in that center. Next slide. We have work going on campus in the Bureau of Economic Geology that looks at cycle analyses, so actually comparing wind and solar and wind, solar, and natural gas batteries. There's a lot of discussion about critical minerals needs for batteries. How do we address those? So we have work going on at UT looking at the overall landscape related to renewables adoption. Next slide. We have work going on in water. So the water use is directly tied to energy use, tied to food. There's a food, energy, water nexus. At UT, we've got some of the world leaders in water research. We have a center, a Department of Energy funded Energy Frontier Research Center on water, on membrane development. So Benny Freeman, Lynn Katz are part of that. So we do a lot of work at UT related to water as well. Next slide. So one of the things that I've been thinking about a lot as director of the Energy Institute at UT is how do we make use of our large-scale research potential capacity. So for example, we have something called the Wildflower Center, the LBJ Wildflower Center just south of campus. And that area, it's the agrivoltaics, solar greenhouses, smart buildings, looking at e-mobility and understanding renewables and biodiversity. So those are some of the activities. Next slide. In terms of renewables and new energy generation, I've talked a little bit about solar. You're going to hear a great talk coming up about wind. We're also looking at geothermal quite extensively on this as a renewable energy resource. Next slide. Some people think about geothermal as a renewable energy resource. They tend to think about Iceland, for example, and volcanoes and that, which clearly have a lot of heat available for extraction. But our Bureau of Economic Geology and Petroleum and Geosystem Engineering Department, Ken Wissian and Sylvia Levesque, have been examining in some detail Texas, for example, for geothermal. And I was just thinking about the Azores, and I bet there's some decent geothermal power capability in the Azores. Next slide. We have a project run by Ken Wissian of UT in collaboration with Houston that's actually developing and demonstrating new geothermal energy production for a military base at Ellington Field. So this is one reason I was thinking about the Azores a little bit. And so I think that there are a lot of potential for geothermal energy production that people aren't thinking about so much. And this is a very active research area at UT. Next slide. So if we consider how energy is produced and the end use sectors. We basically use energy either as electricity, so we call it power use, or as energy production or energy use in terms of heating and that sort of thing. And so if we look at where the energy is supplied versus where it's used, how do we decarbonize the production and the end use? And again, one thing people think about is widespread adoption of solar. In May 2021 of last year, 5% of U.S. electricity was generated photovoltaics. That continues to go up. So as we have more and more renewable generated electricity, how do we utilize that energy effectively, for example, like heating of chemical processes? Next slide. So we're looking at that kind of research at UT. We have a pilot plant for looking at processes. It's called the Process Science and Technology Center. So we're in the process of looking at how to electrify that power plant. So again, how do we decarbonize the chemical processing? Next slide. At UT, we have a lot of work on carbon management, so carbon capture and storage. Next slide. So I don't know if you can you hit the video and let that play? So for example, we have work that's going on in terms of monitoring methane emissions. So this is a really important problem related to spurious methane emissions. First of all, understanding those methane emissions and then creating policies to address them. And so David Allen in our Department of Chemical Engineering is one of the world leaders on this, understanding where those emissions are coming from. It's a challenging problem. It relates to the sensors themselves, putting methane sensors out in the field, understanding how to adequately sense where the methane is coming from, and then figuring out policies of what to do on that. So we're one of the leaders on that. Next slide. So Dave Allen has a research consortium. It's called Project ASTRA with several industry partners where they're monitoring methane emissions in the Permian Basin and trying to understand, is there a way, for example, to create a like clean natural gas standard where you know kind of how your natural gas is produced. Next slide. We've got a really strong effort on point source carbon capture. So Gary Rochelle in our chemical engineering department has actually commercialized a new amine piperazine for scrubbing Honeywell. Has licensed and they're actually deploying it out in the field. So we have at scale research going on point source carbon capture. Next slide. We have research going on the next generation of amines for point source carbon capture. Joan Brennecke, Michael Baldea, Mark Stather. Next slide. Where they're looking at a new class of amines for point source carbon capture of ionic liquids. So Joan Brennecke is one of the world's experts in ionic liquids, and she's working with her team to help discover and develop new classes of chemicals. Next slide. And what they're doing is looking at the chemicals themselves, but then how they would be used in a chemical process. And so both of those are related, and the costs associated with those as well. Next slide. So the research team is examining all the way from the new materials to the chemical process and the economics of that as well. Next slide. In our Bureau of Economic Geology, we have a leading carbon storage consortia called the Gulf Coast Carbon Center, led by Borka. It's been doing this work for years and looking at how CO2 can be stored and managed. Slide. They've been examining, for example, how CO2 can be stored, and then the policy implications. Next slide. And go ahead to the next one after that. So again, they're world experts in the storage and looking at what are the risks associated with long-term storage of CO2, and related to that are policy issues. Next slide. So we have the LBJ School of Public Policy, and we've got some of the, again, leading thought leaders in CO2 storage looking at policy constraints. And so you've got technical constraints, but also policy constraints related to CO2 storage, and we're looking at that at UT. Next slide. And then in our petroleum engineering department, we have a new industry affiliates program that's also looking at carbon storage, but also utilization as well. Next slide. So one of the things that we've been spending a lot of time on at UT is thinking about the upcoming funding from the infrastructure bill. So in November of last year, there was what's called the infrastructure bill that was passed by Congress. There's about $1 trillion in funding for various projects, and a large portion of that is in energy. And so, next slide. So, for example, this funding is starting to come out in requests for proposals. There's a call for about $3 billion of funding in batteries. And this work in the infrastructure bill is really exciting. It's a lot of money, but it's also requiring large-scale cooperations between universities and industry partners. So next slide. So we're working on those things. In the battery area, we're creating a battery research facility to do power manufacturing. Looking at that, and this facility, it's supposed to come online February of next year, is really well aligned with the new DOE call. Next slide. We're also doing materials discovery and development, batteries, but I showed that ionic liquid research. We're looking at ways to combine artificial intelligence and machine learning with rapid, high throughput experimental science. So we're trying to discover battery technologies that go beyond lithium. Next slide. We've got a lot of work going on in hydrogen at UT. So in the infrastructure bill, there's funding $8 billion set aside for at least 4 regional clean hydrogen hubs. So these are really big funding opportunities. We have a lot of expertise on hydrogen at UT. We have a hydrogen at scale project out of the Center for Electromechanics, and also a geological hydrogen industry affiliates program that can form the key components to that hydrogen hub. Next slide. So these hydrogen hubs, I think they're important. So I'll just tell you a couple things. The RFP is supposed to come out on May 22nd from DOE. Maybe there's a way to loop in Portugal into our hydrogen hub efforts. Texas is really well positioned for a hydrogen hub. We're the largest natural gas producing state, so largest producer of renewables. So we have the resources for blue hydrogen, we have the resources for green hydrogen. Next slide. Texas also has the largest hydrogen economy in the US at the moment. Hydrogen is used mostly for petrochemical manufacturing, but when it's produced, it produces a lot of CO2. So how do we take our hydrogen economy in Texas and move it forward to the clean hydrogen standard? Next slide. UT is playing a really big role in that. So we have this hydrogen at scale project that is essentially a demonstration project with over 18 company members, Department of Energy funding, looking at installing at scale, pilot scale infrastructure for hydrogen to understand the techno-economics, how all the various technologies can play together. Slide. So within Texas, we're looking at, so next slide. So within Texas, we're looking at how the different regions within Texas and also nearby New Mexico and Louisiana play into a future hydrogen economy. So we have our local pilot scale test facility at UT for examining new technologies, all the way from materials to actual, field level technologies. And then we're doing the techno-economic analyses to see how these things can fit together in a hub or in a local ecosystem. Next slide. So, for example, we have resources like natural gas for blue hydrogen, but where that hydrogen would be used, at least now, is in Houston. So, what is the best way to produce and use that hydrogen? That's what we're looking at. Next slide. Geological storage is really important for this, and UT is one of the world's leaders in looking at subsurface storage of hydrogen. Next slide. If you want to think about a hydrogen economy, large-scale storage of hydrogen is critical to that. If we look at the natural gas economy, a lot of that natural gas is stored underground and used, and that's a critical component to the natural gases is utilized, and that's going to be true for hydrogen as well. Next slide. So our GeoH2 team is looking at where do you store the hydrogen? Where can you store it? What are the trade-offs economically, geographic, how close they are to end users? Next slide. And there are some significant challenges related to hydrogen in terms of its mobility underground. Next slide. In terms of its mobility underground, its viscosity, and that sort of thing. Next slide. So we have the
Brian, we have 2-3 more minutes.
Okay, great. I should be able to wrap it quick. So we've got the comparison between natural gas storage and hydrogen. We're looking at that. Next slide. We have examination of how storage of hydrogen will be used in the economy. Next slide. And we've got a wide, almost 79 faculty doing research on hydrogen across the board. So the last thing I'll say, just in the interest of time, next slide, I'll just end on this slide. So we're in the process of creating something called the Permian Energy Development Lab. We've got partners across the western part of Texas and into New Mexico, as well as the 2 national labs, National Renewable Energy Lab in Sandia, and examining this region of the Permian Basin, which is one of the largest energy producing regions in the world, as a living laboratory for exploring energy research at scale. So in terms of thinking about the UT Portugal partnership and going forward, hopefully the PEDAL, the Permian Energy Development Lab, can be part of that as a resource as well. So anyway, happy to answer any questions if there are any. Thank you.
So much, Brian, for your very insightful presentation. I'm really sorry that I had to ask you to curtail your presentation. I don't know if there are any questions from the audience or in the YouTube chat. No? Well, I mean, we don't have much time for discussion, but I mean, I cannot afford the opportunity to ask you something. So in your presentation, you highlighted a number of very significant research results coming out of these research projects, initiatives that UT Austin is committed to. I think that we're all very much aware that there is an urgent call to action on climate change. And bearing in mind there is so many research knowledge available to tackle, for instance, climate change through energy transition, I just wanted to ask you, what is missing for us to ensure that these research results turn into ready-to-use solutions that will help us accomplish this energy transition, Brian?
The thing is an understanding of how to collaborate between universities and multiple industry partners and government partners. So I think Portugal program is actually a perfect framework for that. I think that the challenges are so huge and so important to society that the companies need to learn and understand and value the the benefits of collaborating with multiple companies and multiple universities on these large scale projects, and not thinking about just in terms of my own company and my own benefit, and realizing that by helping solve these problems across like an entire value chain of industries, that everyone will benefit, so including society. So I think that's what's missing, is figuring out those complex partnerships between multiple businesses across the value chain and an industry, and how to collaborate with universities effectively.
Okay, so what you said is that this is a process that convokes everyone to come together and find common solutions to this problem. So a very highly participatory process. Thank you so much, Brian. I mean, if any of our viewers want to ask any questions to Brian, they can send us an email, and then I will forward to you those questions. Thank you so much, Brian. Okay, so I think we can now move on to the next presentation. And I don't know if Lance Manuel is connected. Lance, are you there?
Yeah, Andrea, nice to see you.
Good to see you, Lance. Thank you so much. Thank you so much for being here. Next time, I hope it will be in person. So Lance, let me introduce you to our audience. So Lance Manuel is the Texas Atomic Energy Research Foundation Professor of Engineering and Associate Chair of Civil Engineering at UT Austin. His research deals with the modeling of uncertainties affecting the safe performance of civil infrastructure and energy generation assets, with specific focus on improving the safety of wind turbines operating in complex inflow turbulence and in extreme climate events such as thunderstorm, downbursts, and hurricanes. Lance is the principal investigator of one of our projects, the SOS Wind Energy, and he will be presenting about the project. So Lance Manuel, the time is yours.
Thank you, Andrea. Should I run my own slides, or I can do that if that's all right? Okay, someone's going to advance the slides, right? Well, thank you for the opportunity. I can't see the slides so well, so I'll just, I see them a little bit fuzzy, but that's fine. It's great to have had this opportunity the last year and a half. We got a little bit of an extension because of COVID, to work with a group in Porto and 3 PhD students on this project. Over the years, we've done a lot of wind energy, mostly supported by Department of Energy, National Renewable Energy Laboratory, Sandia, etc. But this was nice to have a transatlantic cooperation, or collaboration, I should say, with the group that I mentioned. Oh, wait, it looks a lot nicer now. So this project began with the idea of, if you transfer the, go on to the next slide. Yeah. So there's a lot of decommissioning activity taking place, not so much in the Gulf of Mexico, but in other parts of the world where there's offshore oil and gas, where they are transitioning to other needs. There is a lot of decommissioning taking place in oil and gas in Gulf of Mexico, but not for wind yet. The possibility, though, as you can see down there, to try to not dismantle and waste a product that's in the ocean for other uses has been brought up in many contexts, one of which is wind energy. If you transfer to the next slide. And you can see that both for older shallow water assets as well as for deeper water floating systems, there is a need to find, if possible, new uses for these interesting structures that could support various activity in the ocean, including, like I'm going to talk about wind energy, but also in this new world of a blue economy where we're talking about the possibility of aquaculture and mariculture and mining, etc., to be a base from which you can operate using distributed wind, possibly as an energy. The downside of decommissioning is listed in those bullets there. You have to do so much work to get the site ready for use that it would be nice to not have to do some of that, and maybe clean it up as much as you can for the next use, but not destroy all the steel, etc., that's in there. If you go to the next slide, please. So what we decided to do was, imagine we have an oil platform that's sitting in the ocean, and it's been there for 15 some years, and we want to now think about retrofitting it for possible use for different size turbines that might be feasible. To do that, we first need to know what's the current state. We often don't have information that can tell you the true state. So we are going to try to use climate data from the past to look at what might be the damage accumulated, for example, in fatigue in the various joints and details of the structure. That's in the so-called phase one, in the T0 phase. Then we need to do an analysis for that system that was in place. And then we need to do a new analysis of the structure for an outfitted platform on top of which you would place a turbine. That would usually take a little bit of retrofit, so some initial cost, but increased, if you will, fatigue capacity to endure the next coming loading that you would see. So that on the second phase, when the turbine is installed, and we're doing a study here for 2 and 5 megawatt turbines placed atop oil platform, you'll get different performances in the sense that their reliability will be adjusted based on the load they see in this new system. In this illustrated situation that I'm showing here, the 2 megawatt turbine will have lighter, so will be able to survive for longer periods of time. But in that same period, it's producing less energy, so there's less revenue generated. So we are going to evaluate in step 3 the life cycle of these two systems, and also look at costs in step 4. So that's the sort of big picture view of what this project set out to do. If you go to the next slide, and I'll break it down now step by step. So in step 1, we're looking at typically wind and wave statistics. So in step 1, we're looking at what's called met-ocean or meteorological and oceanographic data. And then we need to look at all the possible scenarios that the platform has experienced in the past and what it will experience in the future. We do in step 2 a structural analysis of the systems under various loading configurations or situations. And then we evaluate the life cycle. So there's some uncertainty quantification involved here, looking at possible use scenarios in the future and what kind of reliability we can expect. And then we need to put in costs. We're doing some benchmark related work with NREL to try to use some data that they've provided to us. I'll break it down a little further down into the next slide, please. So step 1, this is met-ocean data analysis. We picked a site off of Portugal, and you could see in these pictures, you see sort of data in the top 3 pictures of wave height and wave period, which affects the dynamics of offshore systems. And then you see wave height and wind speed, and then you see wind speed and period. Wave period. That's the data from which we then, given the limited data, we do some kernel density estimation of models to describe jointly the occurrence of these various combinations, because that's the kind of data, or that's the kind of mid-ocean sea states that the structures will encounter. If you go to the next slide, please. And so rather than, you saw that the data is not nicely distributed on a rectilinear grid of the 2 variables. It sort of has a cloud shape, which is suggesting that there's a band that may be more efficient to idealize or to represent if you do some principal component analysis. So we establish some manageable number of sea states, 24 for the oil and gas phase, and then 96, where you count 4 different wind speeds over the operating range of a wind turbine for the offshore wind turbine phase. And we look at those various scenarios, and they're going to be used next in our analyses. Next slide, please. So the analysis then looks at a typical detail that's of concern, where damage might be accumulating, let's say at a leg or a brace on the jacket platform, typically a steel platform that supports the oil and gas needs that it had first, and then that will later support the wind turbine. So we're going to analyze all the sea states that I mentioned before and establish what kind of fatigue damage has probably occurred and what will occur in a new scenario where the loading is not coming just from the waves, but also from the wind. Next slide, please. And so this picture, I'm leaving out several details, of course, for this high-level talk. But the parameter on the left on the vertical axis is a reliability index. So your reliability index starts out high, but with time, in the first phase, it falls due to usage and waves that have been encountered and wave loading. And then there's a small blip at year 30, which is assumed to be the year where we retrofit the structure. So it gains a little bit more in terms of perhaps well details that are improved, etc. And then now the new turbine is placed on top of the platform. So the orange curves show a 2 megawatt scenario, and the green curves show a 5 megawatt scenario. In this research study, we looked at various ways in which you combine relative importances of aerodynamic versus hydrodynamic loads on the system. And that's why you see 3 different scenarios. And the next slide, please. So this picture you saw before, and again, it's just showing a little more detail about it. The reliability index related inversely to the probability of failure decreases with time. So the probability of failure increases with time, the reliability decreases. It's retrofitted, it's helped to get some additional safety or reserve strength, if you will. And then the new reliability curves fall off at different rates in the future. Again, this is all based on probabilistic models of first, the mid-ocean conditions, second, the structural response to them, and then some kind of bookkeeping of the fatigue that might be encountered and the possibility the system might fail. So the 2 options, again, in the first option in blue, you see retrofit costs incorporated into the calculations that account for the fact that you're going to try to use a turbine that didn't used to have a platform that didn't used to have a turbine on top. So you got to retrofit it to carry the added weight as well as the possible lateral loads. The second consideration is that the larger turbine will probably require greater amounts of costs to carry this new system. So the platform is going to be heavier. Then there's going to be the fact that because you're going to put larger loads on this new system, in that second phase, it'll last a shorter time, T1, compared to the other case where it'll last longer. But again, as I mentioned before, there's a generation of energy for the 5 megawatt turbine, which is expected to be greater per unit time. Let's move on to the next slide, please. So we account for costs of the various items I've gotten there. I'm going to leave out all the details here, but you can see the definitions related to the various characteristics that I introduced before. There's the capital expenditure involved with the turbine. There's the saved expenditure from not having to waste the old jacket. There's retrofit costs, there's operational expenses, residual costs, etc. And you're accounting for the possibility that the system might fail. So there's a failure probability in the numerator. And then there's energy generated in the denominator. All of this is accounted for, if you go to the next slide, in the 2 scenarios. Next slide. Yeah. And so again, this is data that is still something we're working with to try to make it sort of specific to the needs of our research project. But NREL had some studies, paper studies on various types of turbines, and the 5 megawatt benchmark was used in this case. The 3 cases I mentioned were related to the possible scenarios in the future where aero versus hydrodynamic loads could have different degrees of contribution relative to each other. And by and large, when you do all the calculations, in our case, we found, this is a very simplified overview now for this presentation, that the cost of energy for doing something like this may be feasible in line with expected costs for this kind of asset. But the 2 megawatt turbine was the preferred scenario for what we had. Go to the next slide, please. And so this is a summary. It's basically what we're saying here is in this transition period, oil and gas platforms can find different uses. One use not the only one. We're looking at other possible multi-purpose platforms for other uses as well. But one use we suggested here is to support a wind turbine. And it could be that energy you can use for local needs if you have other activities going on around the old oil and gas platform. And so that's the hope for such a scenario or this kind of research. We use a reliability-based framework. We're accounting for safety, we're accounting for the life cycle. We accounted for retrofit costs and basically said that repurposed jacket platforms can, if you have all the required data, be analyzed in this manner. For candidate turbines, we compared energy generation. This part needs to be refined a bit to be more specific to the needs of an actual project. And finally, the case study was for a port around Lechos, and I don't know if I'm saying that correctly, and so it's saying that if you can get the climate data, if you can do the fatigue analysis for the jacket that exists, if you can investigate reuse scenarios that are possible, and you want to do an optimal design that accounts for life cycle costs, this is possible in a comprehensive manner as we've outlined, and with more site-specific or project-specific information, we could readily include that in this kind of work. And then one more last slide, please. So this is the team. The three individuals at the top are the three PhD students, two at UT and one at University of Porto. And Professor Correa in Porto is the supervisor on that side, and I was supervising our students. I want to acknowledge again the grant that we got, the exploratory grant we got for this work, and thank Andrea and Marco for providing support to this project. I think that's it. There's a slide at the end, which is, I think, the UT Portugal program. It was great to have had the talk, and I'm looking forward to questions.
So thank you so much. Very interesting project, Lance. And thank you as well for sticking to the allotted time. That gives us some time to ask questions. Again, I'd like to know if there are any questions from the audience to Lance. Okay, so again, I have a question to ask you, Lance, if you allow me.
Sure.
So I understand that this project is very much, providing the knowledge just to know how we can use out-of-service offshore jacket platforms. But I was wondering, and this is just curious to know if you have thought about extending this study just to understand if there are any other potential applications for these decommissioned platforms, besides wind power generation. Have you considered other possible applications for these turbines?
For the platforms you meant. So I think the platform itself could be a launching point, given that it exists already in the water, and you'd rather not dismantle and destroy the various materials, etc., that are in there. But other things that have been suggested are some exotic plans like buildings in the ocean. SpaceX is even talking about putting launch pads for rockets and so on. You've been seeing other more exotic things like dive pads and tourism related scenarios where people are trying to look at the possibility of putting in place something that folks could come to learn various aquatic related activities. But in the so-called blue economy that's emerging around the world, there are many ways in which something can serve as a site from which you would do other things. So the question is, what can you do given that the asset is large enough to take pretty large payloads as well as support things like aquaculture or mariculture, mining, as I mentioned before. I also mentioned tourism now and a few activities related to it. These are all things that don't require quite as much retrofit as a turbine would, but they're all possibilities. And I think we've been thinking about those as well. and looking at possibilities for multi-use activities on platforms of this kind, especially the larger ones.
Yeah, I know that, for instance, I think it's in the Gulf of Mexico. Some of these platforms are being used for artificial reefs. So there are many potential applications for sure for these platforms. Lance, thank you so much. It was nice to see you, and all the good luck for this project. I know it's over, but I mean, there's a lot of possibilities for you for the team to move these results along the value chain. So thank you so much, Lance.
Thank you, Andrea, for the opportunity.
Bye. Okay, so now we are moving on to the third presentation, and I think Javad is already connected. Can you confirm, Javad?
Yes, I'm here.
Hi,
can you hear me?
Great to see you. Yes, you can hear. So let me introduce you, Javad. So Javad is an assistant professor in the Department of Civil, Architectural, and Environmental Engineering at the University of Texas at Austin. Prior to joining UT, he was a faculty member in the Electrical and Computer Engineering Department at Carnegie Mellon University. Javad is one of the principal investigators of an exploratory research project with the program seal, and he will be talking about machine learning at grid edge. So the stage is yours now, Javad. Thank you.
Much, Andrea. If you can share my slides, please. Awesome. Hi, everyone. Thank you for the opportunity to be here. And thanks to the support from the UT Portugal program. Prior to joining UT, I was involved in the Carnegie Mellon Portugal program as well, and I truly appreciate the partnership between universities and the Portuguese university systems. So this project that was recently funded, and we started this late January this year, looks at addressing some of the emerging issues that we had related to managing the electric grid and electric infrastructure. If you go to the next slide, please. So we are in the middle of a transition, and our energy value chain is transforming as well. So the way we built our electric grid 100 years ago, it was a supply chain set up with big generators on one end that are producing electricity, and we had end users on the other end, and we usually have transmission and distribution systems in between. And you can think of this as a highway that we built for electrons, a one-way highway for them to get from the supply chain to the end use. If you click enter, can you go to, okay, yes. And but we have a lot of emerging technologies getting connected to the system right now. We have energy storage, we have we have different kind of energy storage. We have batteries, we have solar panels, we have wind power, we have electrified mobility systems that are getting connected to the system. And this system is transforming. And going back to that one-way highway discussion, so now you have a highway that you are allowing electrons from different streets into that highway. So you need a better traffic control that you originally didn't have in the system. So you need to revisit a lot of these decision-making protocols that you put in the system originally, because the system that we designed didn't have this much emerging technology getting connected to it. And this is one of the questions that we are looking at answering this in this research project. What are the needs for what are the decision-making protocols that needs to be revisited? How we can upgrade those, and how we can use some of the novel machine learning techniques to make that happen. If you go to the next slide. So, this is in addition to the energy transition that we see because of the emerging technologies, electric grid also is under pressure to reduce its carbon footprint. Electric grid and energy production is one of the largest contributors to the CO2 emission. And if we want to combat the climate change, we need to decrease our CO2 production dramatically by 2050. And in the recognition of this need, we have a lot of policy changes going on around the world. We have a lot of people working on technological advancements to make this happen. If you go to the next slide. At the same time, we have a lot of resiliency issues with the electric grid in the US. We had Texas grid issues related to a winter storm, and in California we had wildfires that impacted the life of many people and also impacted the grid operation. So we have a lot of resiliency issues going on around the power system. And if you think of an electric grid, that's ultimately a supply chain setup that you want to make sure that supply is equal to demand at all times. And that's the basic governing principle that this system is operating on this foundation. And every other principle that you have governing the system is basically built on this one simple principle: supply equal demand. But that needs to happen every millisecond. That has to be there all the time. So to make that happen, we need to add more flexibility to the system. And we need to remember that as we're adding more intermittent resources to the grid, like solar panels, wind power plants, and all of those intermittencies to the grid, we need to add more flexibility to the system to make sure that we can manage that supply chain need, and making sure that the supply is equal demand at all times. Can you go to the next slide? So one of the issues that we are very interested in looking at, how we can better manage the system. And in order to better manage the system, we need data from the system. Okay, and when I say data, we need data from big power plants, nuclear power plants, big wind turbines, big solar farms. But we also need data from the distribution side of this grid. We also need data from end users. We also need data from substation, and this has become a challenge because of the data volume that we're collecting, also distributedness of the data. We are collecting a lot of data from different points in the grid. How do we manage those? How do we use this for better operating the system? To give you an example, we have a lot of advanced manufacturing, advanced monitoring infrastructure being rolled out by different utilities in the US. And they have a lot of capabilities, but given the data volume that they're collecting right now, those are being mostly used for billing purposes. And they have a lot more potential, but the challenge that utilities are facing, how to deal with the data volume that these smart meters are collecting, how to process them, what will be the best way to keep the confidentiality of the data that we are collecting from the customer. And so that brings up the question of data ownership. Who owns the data? How can we preserve privacy? And how do we deal with the heterogeneity of the data that we are collecting from different customers? And sometimes you have these sensors that are installed in the grid. Their information that are sending, sometimes they're delayed. They cannot be used. So how would you deal with this heterogeneity of the data that you're collecting? And this is really the key for managing the grid. If you want to have a grid that is sustainable and you have a lot of solar panels connected to the system, you need to have a system. You need to have decision-making protocols that can ensure supply equal demand at all time. And to make that happen, you need data. You need data to make sure that to use flexible resources that you have in the system. So this is exactly the focus of this project: how we can leverage the data that we're collecting from the customers, and how we can integrate that into our decision-making protocols. If you go to the next slide, please. So, and if you think about the electric grid, you have a wide range of energy production and consumption resources here. And we, in particular, in this project, we are interested in looking at a bottom-up approach, starting from the end users, looking at the data that we are collecting from them. Traditionally in power system, they have been system in place to collect data from big power plants and managing those. But as on the distribution side of the grid, we haven't invested as much on rolling out sensors, making the system monitoring of the system easier. And but this really needs to change now, because this system is not the rigid system that we built around 100 years ago. We have a lot of intermittent energy resources being added to the system, and we need to manage the bottom of the grid better. And smart buildings and connected communities are really the cornerstone for this future power grid. And the first research question that we're answering in this project is how we can better predict the consumption and production of these smart buildings. And this is really the key for resilient operation of our energy infrastructure. And a lot of traditional approaches that we have for predicting electricity consumption, those are built on those come from the data that we are collecting from the end users, and they often do not include the data that these end users have. So that the question is that data potential, how we can leverage that data to improve the prediction of the building load. The next slide. So for the first phase of this project, we are looking at a setup that we have many buildings. Each building is equipped with a sensor, smart meter, for example, that reads the energy production, and that information would be shared with an aggregator or with a third party, with the electric utility, and that data will be used for building a prediction model to predict the energy consumption of each of these buildings. At the same time, each one of these buildings, they have confidential data, like occupancy-related data, that they're not willing to share with other parties. So the question that we are answering here is how we can build mathematical models that would keep that data confidential, process the data locally at the edge, using the sensors that are located, the sensors and the computational tools that are located at the building, and share the insights with other parties. So instead of sharing the raw data, we will share the insights with other parties. And we have been working on the so-called federated learning models that would enable this data sharing between the parties. And really, that's the first step. So after developing a better tool for predicting the energy consumption of each building, our goal would be now to develop tools that will enable each one of these buildings to better participate in the grid activities. Like, for example, each one of these buildings, they can be scheduled to respond to the grid needs. So if the electric grid needs to shed load in specific hours of the day, they can respond to that needs, and they can depending on the flexibility that they have, they can reschedule some of their local loads. And that's really what we're after, like building a model first to better predict the consumption, and then use that model to build a tool for these buildings to respond to the grid needs and be part of the solution instead of becoming a problem. Can you go to the next slide? So some of the preliminary work that we have been doing in the past 2-3 months is we have been looking at the data that we collected initially from 6 buildings from University of Canberra. We used and those are all academic buildings. So we are using some of the common feature sets like net energy demand from those buildings, whether they have PV generation installs on the rooftop, and what kind of other feature sets can be used from those buildings, class schedules, exam schedules, vacation, and typical data that's used for prediction. Also, we are looking at a specific occupancy data and trying to integrate that with better prediction models. And I'm not going to get into the details of this, but we have been, if you go to the next slide. but we have been testing this, and we have been getting promising results. And I don't know if you see this in good quality or not, but we have been using this model to test for different days and different months and different years of data that we collected, and the model has been showing great adaptability to different setups. And as we integrate more confidential data into this process, the model will improve. But really, the question that we are looking to answer is what will be the privacy preserving setup that would enable this data sharing, and that would ultimately improve the prediction model. If you go to the next slide, please. So in addition to this, as I said, the next step that we are really looking at is after having a better prediction model, we are looking at building a decision-making tool. And one of the way that we envision the future of the grid is having a grid that is, at least on the customer side of the grid, that we have a plug-and-play setup. Plug-and-play meaning that if you have electric vehicle that is going to get connected to a charging infrastructure, and that electric vehicle has a battery, it can charge and potentially discharge their energy. As soon as that electric grid gets connected to the charging station, how can we enable that electric vehicle to share its flexibility with the system? How can we use that battery for better managing this, better maintaining the supply and demand equality? And if you think about the scale of the decisions that you need to make, that will be a very large scale problems, because you will have a lot of these small scale resources, like we will have a lot more electric vehicles coming online. We will have a lot more solar panels, stationary batteries getting connected to the system. So that would be a huge problem to solve, because each one of them, as soon as they get connected to the system, they need to start making decisions. So that would make it challenging to bring all the information that you're collecting from all of these parties to a center and process that information. So the right way to do this would be to have this distributed decision making and information processing setup, that you process a lot of data locally and share insights with others. And ultimately, you have a lot of entities that are talking to each other, and they will come into an agreement, and they would providing the services that would be needed for the grid. So you would have a truly plug-and-play system, and that would enable maintaining the supply and demand equality, and making sure the supply is equal to demand at all time. That's really the key to have a sustainable, resilient grid. And if you go to the next slide. So this is this project I'm leading from the UT side. I have a great collaborator, Pedro Mora from the University of Coimbra. From the Portugal side, we have been working with each other through the academic partnership between Portugal and Carnegie Mellon and now UT for a couple of years, and we have 2 PhD students involved in this and 1 master's student, and we are looking forward to the next year of this project. And next slide. I would like to appreciate again the support from the not the previous slide. So I would like to appreciate again the support from the UT Portugal program. And with that, I would be happy to take your questions.
Thank you so much, Javad. I just have a very quick question, and because I'm being told that we really need to move on to the next speaker. So this is an exploratory research project. You have a few months ahead of you to complete it. So after this project, how long will we have to wait to really benefit from the research you're undertaking currently?
So that's one of the aspects that we are exploring as of now. We are trying to look for partners in Portugal and talking to utilities to see to look for deployment partners in Portugal. I've worked with REN before joining UT Austin as a partner, and I know there are other utilities in Portugal that are potentially interested in this. So we are looking for partners in Portugal and try to see how we can deploy this in the field. And on UT campus, we are trying to also deploy this in the setup that we have on campus, the hardware setup that we have in my lab, to do some initial testing here before deploying this to utilities. But we are looking for partnerships, utility partners in Portugal. So if we have any in this in the audience, I would love to talk to you. So please reach out. We would be very excited to discuss possibilities.
Or other opportunities to move this project along the value chain. So our final presentation will be by our colleague Carlos Silva. Carlos, are you already connected? Can you hear us?
Yeah, can you hear me?
Carlos, very quickly, a brief introduction for our audience. So Carlo has a master's in mechanical engineering from the Faculty of Engineering of the University of Porto. In the last 3 years, he has been working in academia and industry, mainly in research topics related to renewable energy. He's currently a researcher at the Center for Power and Energy Systems at INESTEC, and he will be presenting about Deucalion, our supercomputer that is installed or should be installed very soon at the Minho Advanced Computer Center, and he will be explaining the Deucalion's relationship to digital and green transition and introduce sustainable HPC, high performance computing, the main objectives and preliminary results from the project. So the stage is yours now. Thank you, Carlos.
Thank you. So thank you for the opportunity of doing this presentation. I'm here on behalf of Luís Seca, which unfortunately could not make it. Next slide, please. The name of the presentation. Sorry, next slide. Can you hear me? Yeah, thank you. So the name of the presentation is called Coupling Digital Transition with Green Transition, the case of Deucalion. And I'm going to talk to you about how Deucalion, a high-performance computer, can be contextualized within these two concepts, so digital and green transition. And furthermore, I will also introduce you to the Sustainable HPC project and the preliminary results from the project. So next slide. So, brief context, Deucalion is a high-performance computer which is going to be installed in a building in Ave Park in Guimarães, Portugal. And its installation includes not only the HPC machine itself, but also the surrounding building and the electrical and cooling infrastructure. On the left, you have a map where you can see the building in which Deucalion is going to be installed. In the center, you have Deucalion, and in the right, you have some of the available terrain slots that we have to install our assets, namely some renewable energy systems. Next slide. So HPC are infrastructures that are very used for computing intensive applications in which we have access to large computing resources. And its carbon footprint are mainly due to the computing power itself, but also the consequent cooling power that we need to provide to the system to remove the heat from the computing and assure a safe operation of the machine. So why do we need sustainable practices in the HPC industry? Well, first, there's an emerging computing intensive applications such as artificial intelligence, Internet of Things, 5G, smart cities, etc., which need the access to these resources. Then there's an overall increase in the resource demand from ICT. Then we have the exascale paradigm. So we have access to an unprecedented amount of computing power. And then we have the rising energy costs, which compromise the financial sustainability of projects, of HPC projects. So the usage of HPC results in a large carbon footprint, but also in operational costs. And these factors have to be minimized so that we can achieve a sustainable operation, either environmental or economic. So we can conclude that HPC is a key contributor to the digital transition because we are bringing all this computing power and computing resources. However, its implementation must be tightly aligned with the green transition due to the discussed carbon footprint of the HPC. This results from the interdependency that we have between the computing and energy. Next slide. The main objective of the sustainable HPC project is to decarbonize the operation of the Ucali. This is achieved through a combination of multiple strategies. First of all, we want to reduce the overall electricity consumption of the Ucali, which is above 1 megawatt, by means of energy efficiency measures, for example, in infrastructure such as cooling or software. We want to integrate renewable energy, such as around 1 megawatt of photovoltaics and possibly 600 kilowatt of wind energy in nearby terrain slots, or even integrated in the building itself. And also multiple storage technologies, for example, electrical, lithium, second life lithium, vanadium redox flow batteries, and also thermal storage solutions. We want to optimize the operation and also the allocation of computing resources via a combination of methods. This is our computing management module, for example, via job scheduling, no job level management, and other strategies. We want to design an efficient cooling system in which we can minimize the overhead of the energy consumption by implementing solutions such as free cooling, in which we have, for a large number of hours per year, we leverage on the low ambient air temperature, and we can minimize the power consumption of the cooling system. Next slide. Next slide, please. Sorry, next slide. Thank you. Previous slide. Yeah, okay. So we also want to assess the possibility of using the wasted heat from the computing in the building itself, or even integrate that wasted heat in district heating networks. There's also the objective of developing an energy management system, which we take the assets that we can control in the infrastructure, we take the variables that we can predict. For example, the main one is the grid carbon intensity, and we use that to actively shift the system to low carbon operation. This allows us to promote actions such as self-consumption, the storage of renewable surplus, the storage of low carbon grid electricity, and also load shaping. We also want to assess the development of awareness, incentives, and billing mechanisms for HPC. So we want to coordinate with users and promote behaviors that are sustainable within the HPC digital service. And finally, to propose a living lab in which innovative solutions for sustainability in computing centers can be implemented. Next slide. So some conclusions on the project so far. Next slide. Regarding the state of art of computing centers and its sustainability, a lot of effort in energy efficiency, so innovative cooling technologies, new applications for wasted heat. We also have a lot of initiatives for regulation, for standardization and research in computing centers. For example, EU projects are mainly related to energy efficiency actions within the exascale computing paradigm, and also work on the available metrics that we have. Power usage effectiveness is the main one. We also want to minimize that metric in this project. And there are some examples reported below 1.1. Next slide. Regarding energy management, some examples on how to integrate and manage renewable energy sources in computing centers that mainly focus on self-consumption. This is usually achieved by computing management, for example, with HPC job scheduling or job migration, and also the innovative concept of carbon-aware computing, in which the machine operates as a function of the estimated carbon intensity in the grid. On business models, we found that there are a lot of innovative business models which try to integrate renewable energy and also promote cross-sector opportunities. For example, energy flexibility is an important one, or how to promote the cooperation between HPC and electricity service providers, and also decentralized technologies, how to use them and how to combine, for example, the resources from electricity and computing and markets. Next slide. Next slide, please.
It seems like we're having some technical problems. Okay.
Yeah, thank you. So these are some preliminary results we have from our energy management system we are developing for Deucalion. So the basic functioning is to have a set of forecasts as an input related to renewable energy, the grid carbon intensity, among other variables. We then solve an optimization problem, which gives us some control actions. For example, the set points for batteries or the optimal HPC load profile. And you have here on your left, for example, on the top figure, the varying carbon intensity throughout multiple days, and then the basic operation of the system as a function of that variable. Next slide. And finally, we have here a draft for the energy management system architecture. We try to approach this in the most modular way possible, to allow for higher flexibility, to adapt for new services, new machines. What you can see is some modules related to the forecasting of variables, for example, grid carbon intensity, load and renewable energy, numerical weather prediction. And then you have a module which takes all of these inputs and computes an optimal solution and communicates with a local energy management system. Then this local energy management system communicates with available infrastructure on site, for example, the resource management system of the computer and the battery management system, and also the sensory equipment available. Next slide.
Can I ask you to wrap up, Carlos?
Yeah. To finish, we are on work package 2 and we want to start work package 3. And the next steps for the energy management system is to provide the forecast products, develop the APIs, and to finish the optimization problem, the control framework, and also the communication with the controllable assets we have inside. Next slide, and thank you for your time.
Thank you so much, Carlos. In the interest of time, I will not be, unfortunately, taking in any questions from our audience. Anyway, thank you so much for joining us. This is a very interesting project that shows how well aligned it is with the EU's digital and green agendas. I want to thank you, all the viewers who watched us online, or those of you who are at the auditorium. Thank you so much. It's been a pleasure to host this session that shows that the UT Austin Portugal program is well positioned to speed up the green transition, the energy transformation that both Portugal and Texas are committed to realizing. Thank you so much. Bye-bye.